All right, thank you very much. So my name's Andy Gleadall. I'm a lecturer at the University of Loughborough University. And by history, I came from sort of biomedical materials and then 3D printing these materials for tissue engineering scaffolds. And then more recently moved towards more fundamental mechanical properties analysis, mechanical engineering of these. But there's kind of a link between all of these aspects. So in this talk, I'll be talking about bioprinting and giving an overview of the overall process, what it means, but also talk about what that means to engineers as opposed to, say, biologists or medics. So I'll briefly introduce tissue engineering. You can see on the screen here, this is an example of a bioprinter with 4 different syringes, which can be used to print 4 materials in this well plate that's on the print platform at the moment. So I'll briefly describe the tissue engineering and then introduce some of the additive manufacturing technologies. I know Vadim went through those earlier to some degree, so I'll only go through them fairly briefly. And then talk in more detail about bioprinters and show a couple of videos from some bioprinter manufacturer or a bioprinter manufacturer about their system, kind of talk through that, and then go into the details of how those systems actually work. So tissue engineering, it's typically involves a scaffold. So you can see on the right hand side, this is an image of 5 different scaffold geometries. The top row is showing a CAD model of what we're trying to print, and then the bottom 2 are showing different zoom levels for the actual 3D printed structure. So we want this porous mesh, 3D mesh type structure, and that's typically made out of a polymer that's going to degrade over a period of weeks or months or years while the cells are forming tissue. So once we've got that structure, the key thing is then to add cells. Then we culture them, keeping them at 37 degrees, making sure there's media with food that the cells can have and taking away the toxins they produce. And eventually those cells are going to replicate themselves and start forming more mature tissue and excreting the proteins or whatever is required to actually form this tissue that you're trying to produce. So that might be a cartilage type tissue or bones, and whatever structure that is, often the cells will produce the structure around them whilst they're going through their normal lifetime of reproduction. So it can happen inside or outside of the body. You could put one of these scaffolds into a human body, potentially even without any cells, and the body might grow into it. So you see that for some bone cements. Typically in tissue engineering, you would be looking at adding cells yourself as well, and often doing it in a laboratory condition. And at the end of the day, the point of it is to have this new tissue that we can use to replace tissue in the body. So that might be if somebody's had some facial trauma from a car accident or something, then we might need some new cartilage to build up the cartilage that's been destroyed. Or if somebody's had some bone removed, if it's had cancer or something, then we can grow that bone that's been removed and replace it. That's the kind of application. So then types of 3D printing, there's 7 main categories. I think Vadim went through all of these. So just very, very briefly, vat photopolymerization is when we're going to have a bath of a polymer that we're using a laser or some other light source to selectively solidify, effectively curing the monomer into a polymer chain that is then a solid. In the second, and that's done layer by layer. So you'll solidify one layer and then move the print platform down into the vat and then do another layer and so forth. The second is powder bed. So instead of having a bath of resin, we've got a bath of powder, and then we'll use the laser source or some source of heat to actually bond those powder particles together. In the third instance, binder jetting, it's similar, but instead of using heat to bind those powder particles together, we'll be using some other material, sort of a polymer or something that has been ejected from a nozzle to fit in between. So that's kind of like a sand castle. You've got dry sand, and then you use water to just bond those sand particles together enough for a sand castle to have structural integrity. That's effectively what it's doing, but obviously using more advanced adhesives than water. In material jetting, kind of following on from biojetting, but without the binder, without the particles. So you just jet that material in a very precise manner. Quite a slow process and expensive, but you get really good resolution because these little droplets that are being jetted around are really small by comparison to something like extrusion, which I'll come to in a second. Sheet lamination, where we have lots of sheets of material that we cut out a shape on each sheet before we bond them together. The idea being then you can pull away all the bits of the sheets that were cut, and you'll be left with just your area that was designed to be solid. Material extrusion is kind of like material jetting, but we're now extruding material from a nozzle and kind of depositing it straight away as it's often kind of a melted polymer or a gel or something, and it's not jetted in lots of discrete droplets. It's extruded as a kind of continuous filament typically. And then the final one is with laser particles and an energy source with powder particles and a laser source or heat source, melting those powder particles together instantaneously. So for extrusion 3D printing, as I've just mentioned, it's very similar to a hot melt gun. So hot melt glue gun. If you've got that glue in a solid stick form, it's coming in the back of that glue gun. It's then being melted and extruded through the nozzle, and the nozzle is moving around as you need it to put that hot melt glue where you want it. So it's a very similar process, except the glue gun is much, much smaller and it's mounted with rails or on a robot for bioprinting. So I'm just going to show a video. If this is particularly poor quality or anything, then just let me know and I'll try to find another way. So this is a glass slide on the print bed, and then there's a long metal nozzle which is extruding this gel material.
Yeah, so this is fine. It is fine.
It's fine. Okay, so this is a Regenhue printer that I showed you, or one of their printers that I showed you in the very first slide, and it's showing a typical kind of scaffold that you might produce. So that's the basic extrusion process for 3D printing. In this case, very simple structure, but very difficult to manufacture with any other process. You wouldn't be able to take a cylindrical pellet like was shown at the end of that video, if I just go back, and machine this structure out of it. That wouldn't be possible because of those tiny little pores in between layers and so forth. So although it's a simple cylindrical type structure, what we're really interested in is this micro scale geometry in between the filaments and those pores, and that's what we're using the bioprinter for. Okay, so then bioprinting is a sort of variant of extrusion 3D printing, and I'm going to show you a couple of videos now from a manufacturer that's going to go through quite a few of the aspects of firstly the hardware, the bioprinter itself, and secondly how we use how we use it. So basically telling the machine what we want it to actually print. So this is the BioX printer, and you can see it had three different print heads. It's also got quite a few different options. So you don't need to just use print heads. You can use a UV curing lamp or some kind of just a camera, whatever you really want. You could mount onto these printers. This is obviously a commercial system, so they've got their chosen hardware that they allow you to print. And typically you'd have a thermoplastic print head, which would be very similar to what we'd normally use on common 3D printers that you'd have in schools and universities all over the place. And then a syringe pump printer, print head, which you can fill the syringe with a gel or a molten polymer if the syringe is heated. And then you'll just push the end of the syringe in, the plunger in, using a motor. Whereas in the thermoplastic one, you typically be forcing either a filament reel into the back of it, or you'd have pellets in a screw mechanism on the inside. And this is showing a different variant. Often bioprinters will have several different technologies, several different print heads, and combine potentially material jetting. And this is showing the UV curing. So UV curing is very common for bioprinting because the gels that you'll use will often be quite, not very viscous, so they're very runny, and they want to be runny for several reasons, but particularly to get the material to flow through this long, thin nozzle without having a high shear rate. Because if you've got high shear forces, that can kill the cells. So you'll typically try to have a material that is as runny as absolutely possible while still maintaining a reasonable structure once it's printed. So you don't want it to just ooze into a sheet of like a puddle. So you'll kind of have this balance of having it nice and runny for the cells to be happy, but then stiff enough, viscous enough for the structure to actually maintain its shape. So one trick they'll use is printing with a nice runny material, and then as soon as it's printed, after each layer, they'll cure that material using UV light. So that will convert the gel into a more solid gel or a completely solid gel after it's been printed. And there are some gels that won't set at all unless you have a UV source and polymers. So you saw then the print heads, one moved up, one moved down, and that's just a logical benefit that you're not going to have the previous print head kind of crashing into the structure as you're printing. It's not always required. You can have printers where the multiple print heads are all constantly at the same height, and you just have to try to avoid putting these print heads at the side into the structure if at all possible. If you're printing in well plates, that would become really, really challenging. But on a typical structure where you're printing it layer by layer, all your nozzles should be just slightly above the structure that you're printing anyway by one layer. So it is possible. And yeah, a real key thing for bioprinting is very often using multiple materials. So you can see here, we've got three different, or potentially three different materials. And there's one at the perimeter, and then one is the grid, and one is just being deposited as little blobs in each of the cells. So that might be the case that in bioprinting, you might want a slightly different type of cell around the edge. So you might want to have skin cells around the edge of the structure, and then you may have a combination of, say, some soft tissue and some vascularization in the middle. So you might want to have these blue lines might actually act as blood vessels or something like that. So you can have these different combinations, or just some of them might be just for structural purposes, and then the blobs might be the bits that have actually got cells mixed in with that gel. So yeah, I don't think I truly mentioned, often you'll print the gel and you can actually have living cells inside that gel. And this is just showing what some of the more recent, more advanced systems will have this automatic calibration. So in this case, they've just got a post that they're pushing the print head up to check for its X and Y location. When it hits the post, it will know now exactly what location the print head's in. Some will use a laser to actually detect the print head and move the print head down towards the laser. And they'll be able to measure from that laser exactly how far away the print head is. This would just be to make sure that if you try and print, as we showed before, with a structure like this one, if the print heads, the three different print heads weren't correctly aligned, then we could get a shift. So all this blue grid might not match up perfectly with the outer red grid, and these droplets might have been printed on the intersections rather than in the grooves. So that's an important aspect. And then that was showing an the desktop software, which I'll show in the next video. On the slides, you'll see the text for the YouTube link is hidden now that this has become active, but the text for the YouTube link does flash up as soon as I change slides, and on the downloadable slides, you have got the links for these videos to watch them in higher quality. So this is the same printer, and then it's going to talk about how the user actually gets it to do what they want. So the first thing you'll do is import your 3D model. So an STL file is a very, very common file format for a 3D model. You can create your 3D model in CAD, or you can take some medical scans of a patient and obtain the surface, the 3D surface from those scans, for example, of an ear, and then convert that into a STL file, which is just a 3D model file which shows you where the surface of an object is. So that's a preview of the STL file. You then have to select all the details about your printer, what materials you want to use and that sort of thing. In this case, for a bioprinter, they'll typically print in several different options that are added onto the printer. In many other printers, you'll just always print on the print bed. So from normal extrusion additive manufacturing printers, you wouldn't put a weld plate on those printers, you just use the print bed. But for biomedical applications, because you're often then going to treat these printed structures with cells, or put cells onto them and put them in culture ovens, that's why you will put in a new plate each time. So this is then saying you can choose your 3 different print heads, which ones you want to use for this model. And then for each print head, you can choose the material. So a common thing that you might use is one material might be used just to create some support for the other material. So if we haven't got a nice flat bottom of so for example, the ear, then you can't just print it in the middle of the air. You've got to print on top of something that's already there. So you might print the sort of mold of that air almost underneath to support then when we print on top of it. I'll show you that in more detail in a future slide. So then there's going to be lots of different aspects of your printer as well that you can control. In all cases, there's going to be if you're printing a melted polymer, there'll be the options to have fans to cool that. There'll be the options to have a warm print bed, and that will mean that the material will stick to it a little easier rather than cooling very quickly and then it has a tendency to peel off. So there'll be lots of different print settings that really depend on the printer. And in this case, it's talking about whether to use the chamber fan for cleaning the chamber and the print bed temperature. Others will have temperature of the air inside the chamber and that sort of thing. So then this is now saying for each layer that you're printing, you're going to slice your 3D model into lots of layers. And then for each layer, you'll get a choice of how you want to print that layer. So the easiest way would be just to slice your model into lots of layers that represent the cross section at various different heights of that model. And then you can just put material to fill those cross sections layer by layer to get the actual structure you want. They chose a honeycomb pattern, which I'll show later on. And then it's just showing some of the extra options that you might want to do some manual control of the printer, to do some tests and to calibrate it and make sure everything's all lined up nice and neat. Okay, so that's an introduction to the bioprinting process with quite a lot of them, and now I'll go into a bit more detail about the various aspects. So typically you'll be using a scaffold material, and then you've got to get your cells on it. So you could just have a scaffold material that's made of a polymer or a hydrogel. It's given a couple of examples of the polymers that might be used and some of the hydrogels that might be used. So these are naturally sourced from the body, whereas these are obviously created either from oil or from things like sugarcane. So then you'll create your scaffold, and you can either put cells on it after you've manufactured it. So this would be you just put your scaffold in a media containing cells, and the cells will gradually flow through your scaffold and attach to it. And then the other option is to actually have those cells captured within the gel that you're printing, like I mentioned before, and then they will gradually grow and multiply within that gel, and potentially also move around within that gel to if they're attracted to, say, the polymer material or something that they're connected to. Typically they're not attracted to the polymers. They'll actually prefer to stay in the gel. But then, yeah, that's a sort of the overview of the process. And now some of the more engineering details is what I'm going to go into here. So for our extrusion system, I briefly mentioned this, but this is going into a lot more detail, the different options. So at the end of the day, we want to get material to come out of our nozzle. I'm referring to it as an extruded filament, because as the nozzle's moving, that material is coming out and being laid down as a extruded filament. For most commercial printers that you'd see, just like automakers or maker bots, they would use a filament reel as the feedstock. So you'd buy a reel of filament, just seeing if I got one here, and then in any case, then that's going to be fed into the back of the melt chamber. The melt chamber is going to have heaters on and temperature sensors, and it's going to be kept at a temperature that's above the melting temperature of the polymer. So as you force that material, that filament reel, into the melt chamber, it's going to become molten, and because you're forcing it in the back, you're creating a pressure which is extruding the material from the tip, from the nozzle. Another option that's not often seen, but potentially sometimes seen in bioprinters, is a screw extruder. And in this case, you can feed in pellets, and then there'll be a screw that will force the pellets, after they've been liquefied, melted into a molten polymer. It will force them by turning this screw out of the nozzle. So you don't need to buy your material on a filament reel, and that's why this is quite good for bioprinters, because often they're using one-off polymers that are just being used for research and have never been printed before. So you can't buy it in a filament reel format. You can buy it in pellets or powder much easier, or much more commonly. So then it's much easier to get the materials you want in a format you need for printing. And then the final one is using a syringe. So this can either be with a motor that's driving the syringe, and then you'll tell that motor how far to plunge that syringe in, and that will dictate how much material is coming out. The other option is to apply pneumatic pressure. So you just have connected to your compressed air of some sort, either a cylinder or the main system, and you can vary that pressure to vary the speed at which material is going to come out of the nozzle. And these options are often used for gels, but they can be used for polymers. If you put your pellets in here first, heats the whole syringe up if it's in an enclosed housing, and then once it's all become molten, you can then plunge it, and just making sure you keep that syringe at the correct temperature. And then the overall process that was briefly touched upon in that second video from the BioX printer, you get your 3D model, you'll bring it into your slicing software, into your 3D printer software. it will convert that 3D model into cross-section slices. This is what I'm showing here. This cube has been sliced on the horizontal plane 8 times or 7 times to get these layers. And then for each layer, it's going to analyze that layer and determine how to move the nozzle around to fill that layer with material. And that's our print path for one layer. So then you'll combine all your print paths for every single layer, and that's going to give the total print path that you need to print your whole part. And that's basically exported as G code, which I'll just discuss here actually. And that's just a list of instructions about how the printer can achieve that print path. So in this example, there's a G code command is G1, X10, Y10, Z 0.5, F1000, E 0.5. And the command, the first bit of that line is saying move. That's what G1 means. The next bits are saying what the XYZ coordinates are that it's moving to. This bit, the F speed, is telling it how fast the nozzle should move while it's printing to this new position. And then finally, the extrusion amount is while it's moving to this position, how much polymer should we extrude. So that's what the G code actually looks like. And each one of these segments of our print path will have its own line of G code, which will say, this is what you've got to do now, printer, to achieve my segment. So I'm going to give a very quick demo of Cura. So this is slicing software that's used for automakers, but it can also be used for many other printers. People do use this software for bioprinters just because it's convenient, it's free, it's quite powerful, and you can export the G code in a format that your bioprinter can use depending on the bioprinters. Some will be proprietary control languages, which you can't export from Cura, but in many cases you can. So then I've already downloaded an STL file, which is this cube.stl, which I'm just opening in some STL viewer. And that's what the STL file. It's a cube, but it's made up of triangles because STL files have to be triangles, and it's just using 2 triangles to create one face of our cube. And all those triangles are just linking the different coordinates of our corners to say this is our 3D model of a cube, and it'll be hollow on the inside. I kind of zoom in, you can't really see. It's just a surface. So then if I drag that into Cura, it's now put it on the print platform, and then if I click slice, it's then going to convert this cube into lots of layers, identify all the print paths for each layers, like I said, and then generate the overall print path for the whole structure. So then if I preview it now, we can see this is the print path that it's generated for this structure, and it's doing it layer by layer, and it's a triangular type infill. And I can look at individual layers. So on the right hand side, I can show which what just the bottom layer looks like this, the second layer looks like that, the third layer looks like that, and then we just repeat those over and over and over to achieve this triangular grid. And you can also see the order in which each line is printed on the layer. If we come down here, let me just drag it manually. This is going to show the nozzle moving to print the first line and then moving across to print the second line. And it's showing you the exact order and direction which each layer is being printed. So this is a really nice piece of software to visualize your tool paths or your print paths and see how is it doing it. So this layer, it's not necessarily printing it in the way you'd expect. You might expect it to start in one corner and then do lines this way. What it's actually doing is starting on the middle of the side there, or starting in this bottom corner and then coming across, and now it's going to fill to the bottom right, and it's going to quickly jump all the way from that bottom right position to the start of the next line up there. So it's got to identify how to print the layer, and then it's also got to identify the order in which to print all of these lines. So in this layer, it is managing to do it in one nice neat go. So this is your slicing software, and I mentioned different types of grids that you might use. So this is using a triangular grid, although it's just actually parallel lines. They're rotated for each new layer by the amount that I've entered here: 0 degrees, 60 degrees, 120. So if I just did 0 degrees, which would mean the X direction, let's say, or the Y direction, and 90, now the grid is just going to be a square grid where the lines are printed at perpendicular to one another for each layer. So if I slice that, now we've got our grid. One sec. So that's our grid structure now with the grid orientated in the X and Y. We'd also have quite a different structure if we printed it at 45 degrees and then 135 degrees. So we'd have a diamond type grid. It's the same structure, but in terms of our orientation with respect to the the overall cube, it will change things. So then that's going to be our diamond one. And there are various other ones. So this is using a lines infill pattern. There are all of these different ones. So a gyroid's quite a nice one to visualize. So for this one, then each layer is changing in this way. Let me get you a better angle. As I come down through the layers, you can see how each layer is printed slightly different, and it gets this nice gyroid geometry at the end. And again, the way that each layer is printed, it's not that much more complicated than printing the lines like we did before. It's just wavy ones instead of linear ones, but just by varying those lines in an interesting way across each layer, you can end up with this nice 3D structure in the end with kind of interesting pores in different directions and so forth. So very lots of different types that you can print in terms of infill. Some are more suitable to biomedical applications where they have got porosity going all the way through, and others are more suitable for mechanical applications. So that's Cura, and it has a lot of settings on the right hand side. I'm not even showing the majority of them here. This is probably only maybe a tenth of the total number of settings that it would let you adjust. So each one of these sections is talking about a different type of thing. So the one we were talking about with an infill, then we can change all these settings for the infill, but we might also want to change it so it's got a wall on the sides, in which case I can just put a 1 millimeter wall on the side, and then this is going to give it a shell at the side. So there's lots and lots of different customizations you can do in Cura. So now we've got our solid wall with our infill inside, where the nozzle's first going to print the internal structure, and then once it's printed that, it then prints this outer wall, and then that's the layer complete. So lots of different settings, but they don't have settings that are really optimized for bioprinted structures often. So in this structure, we want lots of different materials for each different line, and we're also moving the nozzle to inject a bit of material in each of the grid's cells. And Cura doesn't really have an option for that. So there is software for bioprinters where you can actually design your print path by drawing the individual lines and then choosing a material for them, and potentially other operations like those points are representing just an extrusion of material. And then it will still do, the software will do a lot of the thinking for you as well. So if you've drawn all these green lines, it might then decide the best order to print them in. Because if we print this line down here, the nozzle's now got to get from the end of it to the beginning of this one, or this one, or this one, or wherever it's going to go next. So it will still do some things in an automated way, but you have a lot more control over the layers print path. And then you can kind of define the different materials for each layer, and then how this is going to happen for multiple layers. So this is sort of bioprinting software will have some of these aspects which allow a bit more manipulation of how you want those nozzles to move around and extrude material. And this is showing a nice example of, if you need even more control, then people will typically write a script that would automatically calculate the print path or determine the print path without using slicing software or bioprinting software. They would just manually identify the print path, every segment of it, and what material and the order and everything. So this is much the same as what I was showing before. You've got a 3D model, you're splitting it into layers and then identifying the print path of each layer. So let me zoom in. So this 3D model is an ear. We've also got this yellow bit is support material, so that we're not printing the ear kind of floating in this tip of the ear would be floating in the air otherwise. So then that's our model that we're trying to print. It's split into layers here, and then for each layer we're getting our print path. And then we've got multiple different materials. They're saying they've got 2 different hydrogels, which might have 2 different polymers in. They've got the polymeric scaffold, also support material to support those layers subsequently above it. So we get this quite complicated print path, but it's automated to some degree. So this would be achieved by writing software or a script where you can actually effectively do the job that Cura is doing, but with a bit more freedom. So then moving on to the mechanical performance, there's a wide range of materials that can be printed. This is just showing some of this vast different elastic moduli that can be achieved with hydrogels, polymers, or ceramics, similar with strengths. If you want more details about this, then this review article that I've mentioned here, which I think I've uploaded, has a lot more detail, but typically they capture some of the range of properties that you'd expect in different tissues in the body. So your choice of material is by far the most important thing that's going to affect your mechanical properties. But then once you've chosen your material, you've then got this structure that you're designing and 3D printing, this mesh, this 3D grid that is going to affect mechanical properties by a huge amount as well. So even if we've got a certain material, the material choice might be constrained by other factors, like if it's got to contain cells, then we can't be using a polymer. It's got to be a gel. So, or normal, let's say it's got to be a hydrogel polymer rather than a synthetic pure polymer. So then this is showing 4 different grid structures, like I showed you in Cura, and then the cross-sectional view of them. There's also, in this case, the grid is offset. So rather than here where the grids, the line's going horizontally and the line's going vertically in the 0 and 90 degrees direction, according to this axis at the bottom. This one, they're actually offsetting it. So each time we print a layer of vertically oriented 90 degrees filaments, they're shifted. So on one layer, they're going to print this line, and then the next layer up, or 2 layers up, they'll print this line and this line. So we get this staggered nature, which you can see on the right-hand side here. And then there are options also to print, rather than what we saw in Cura, where we had filaments in one orientation and one layer, and then the next layer it changed, and the next layer it changed. In this case, they've got 2 in the same orientation, and then 2 in a different orientation, and then 2 in the same orientation. And that can mean we get larger pores and on the side view, which can be really useful for cells, but it will also affect our mechanical properties, as will this staggered nature. So then this is a very brief quick and dirty FEA analysis to show if we've got staggered filaments as opposed to filaments stacked perfectly on top of one another, then the amount of compression, so we applied the same force to this structure and this structure, and that's the amount of strain that was the displacement that was achieved. A huge difference, because this structure can concertina, whereas this structure you've got to crush these columns of solid polymer. So this type of, and that's the models that we use, this type of effect, it's quite easy to see from an FEA simulation on this simplified structure, but it's a lot more difficult to infer when you've got these sorts of images, which is what typically you'd be looking at as an experimentalist, especially this triangular one, where the side view really doesn't capture the information about what's going on there. So the structure that you're printing has a huge effect on the mechanical properties as well as the material. And again, more details, if you're interested, go and look at that review. And I go into a lot more detail about how that the alignment of the filaments might affect it. And there's obviously a strong link to porosity. If you've got a material which has got 10 times as many filaments in, then it might well be 10 times stiffer and 10 times less porous, and that sort of relationship. So then a final little point is this, the potential to simulate these mechanical properties. So this is showing a video animation of a recent simulation method we developed, which is taking a print path and simulating the polymer extrusion. And at a crossover point, you can see slight bulging, and you can see it here on a larger scaffold. So when you've got more obstruction and a larger bulging, then you're going to get, from the FEA analysis is showing how you'll get a much larger area of material that needs to be sustained, that can sustain the force. So you'll need to put in much greater loads to achieve the same amount of displacement, and therefore have a stiffer structure. So this type of simulation can give a prediction, or at least indicate what the mechanical properties of different tool paths might be. So as I've mentioned before, the review paper on tissue engineering scaffolds is a good place to get more information about the mechanical properties and various other aspects I've talked. There's an upcoming book chapter which I've uploaded, and then I added a couple of papers that are relevant, including the two of them which are linked to my students, PhD students, who gave talks on slightly different topics from their papers, but definitely related. So you can see their talks from the conference with these links. And also, if anyone does 3D printing and they're interested in printing really intricate structures with a lot of control, then have a look at a recent presentation I did on the research we're doing to really generate print paths that are not achievable with the normal software. Because as I've said, people already have found this as a problem, where they are writing their own scripts to generate the print path. And in this case, this is just another solution to that problem. So thank you very much. I'll see if there's any questions.
And there is a